Okay. So hello everyone. Welcome to our seminar. Today we have the pleasure to have with us Namita Uppal from the Physical Research Laboratory in Ahmedabad, India. Namita just finished her PhD, and she has worked on many different aspects of the structure of the Milky Way galaxy. She has used different tools to probe the structure of the Milky Way galaxy, and including polarimetry, which is very close to our heart. So today, Namita will explain her findings or shedding some light on the structure of the disk of the Milky Way. Namita, the floor is yours.
Thank you. Thank you so much for the introduction. So before starting the talk, I would like to thank you for giving me the opportunity to talk about my work. And I'll start my seminar now, the work that I have been doing in the past 4 or 5 years with the background picture. This is the night sky view of the Milky Way galaxy. So this is a picture taken by my supervisor. Here we can see there are a lot of dark lanes and bright glow. So all these are the part of our Milky Way galaxy. Now, Milky Way is our home galaxy and we are living inside the galaxy. So it is more easy to access each and every star and study them in greater detail as compared to any other external galaxy. So this galaxy, if we wanted to understand the formation and evolution of the galaxies in general, so this our own galaxy acts as a Rosetta Stone to understand that. But for that, before going to the formation and evolution, one should know the structure of the galaxy. Because we are living inside the galaxy, so we cannot see the complete structure, but we can see only this kind of view in the night sky. So how our galaxy, our own galaxy looks like, we do not know. But there are many observation and theoretical models which explain that our galaxy is a disk galaxy and has few spiral arms. It should look something like the right side plot. So this is a spiral, there are spiral arms, and this is an artistic impression of our galaxy. This is not a complete structure that we observe. This is a based on some data. The extrapolation of that data will give this artistic impression. Now, from the observation, how to construct this kind of structure, this is the aim of my studies. So to construct a 3D map of our own galaxy. So first question come to mind, how we can do that. So I always like this example, like if you wanted to trace the forest by sitting or standing in the middle of the forest, so how can you do that? So the first and foremost thing, if you know the distance and location of each and every tree in the forest, then you can construct a map and you will get a complete map of the forest. In the same way, a galaxy is composed of star, dust, and gases. If we can somehow trace this star, dust, and gases, then we can find the structure of the galaxy. But for that, if we want to trace the stars, we need to know the location as well as distance of each and every star. But in astronomy, we know that distance information is very hard to get. It is very challenging. But there are some indirect way where we can find the distance of some subpopulation of stars, but not a complete, every star will not get the information of the distance. But recently in 2014, 2015, the space-based mission was launched by European Space Agency, Gaia, and it has given a parallax of, measured the parallax of 1.7 billion stars. And they have provided us with the accurate distance of many stars. So this Gaia space-based mission has revolutionized this field and has provided many good results related to the structure and the chemical evolution of the Milky Way galaxy. But to put everything that was done earlier in the past few years in one picture, so here this plot represents the face-on view of the galaxy, where we should see some spiral arm. Here, each and every symbol here represent the distribution of different traces in the galaxy, like giant molecular cloud, high mass star forming region, H2 region, O-type star, and galactic open clusters. So here we can see that there are some overdense regions there where density is very high. So these overdense regions are correlated with the spiral arm of the galaxy. So as a simple model has been fitted on these data points to see how many spiral arms are there in our galaxy. So there is the indication that or direct observation that there are multiple spiral arms in our galaxy, but we cannot see the complete spiral arm information that I have showed in the earlier slide, where we have seen the artistic impression of the galaxy. So these are only small patches of spiral arm that are getting traced, not the complete arms. So not the complete information is there. Some information is missing. And also, if we talk about Gaia has provided us a parallax of 1.7 billion stars. But the good parallax measurement, where the distance accuracy is very good, we can probe only to the distance up to this marked by this circle. So only the structure that are present in between this circle is can get traced, but not beyond that. So again, there is a limiting information. So the goal of my thesis, or the work that we were doing, is our goal was to trace the spiral arm of the galaxy. And here I wanted to emphasize that uh, all these traces that are placed here, these are belongs to the million-year population, the younger population. But our galaxy do have older population. How they are distributed? So there is very less number of papers or the literature where people have targeted the older population. So how they are distributed, and if we know the distribution of the older population, we may get some information about the structure of the galaxy. And also, if we link those information with the younger star information, then we will see how the galaxy has evolved till now. So the distribution of older population is equally important as and comparison with the younger population will give us the evolution history of the galaxy. So with this in mind, we wanted to trace some older population. And also here the number density of the stars or the population that is presented here, they're very less. Like open cluster are the maximum, but only few thousand of open cluster are being plotted in this plot. So number of stars are very less, based on which we are getting the information about the this spiral arm of the galaxy. But our galaxy have billions of stars. So the requirement to choose the population is that there should be different from the this population that till now it is up to millionaire population. So we want to go ahead with the some older age population. And second, they should be numerously present in the galaxy. And third, and most important, that they should give us accurate distance measurement, so that we can make a complete map of the galaxy. So based on all these three criteria, keeping all these three criteria in our mind, we choose to select the red clump stars. So these red clump stars are very low mass stars with less than 2 solar mass their mass, and they are core helium burning stars, and they are numerously present in the galaxy. They have very unique property that they show nearly constant luminosity and surface temperature during their course of evolution. And these are giga-year population, so they are intermediate age population type of stars. And because of their constant luminosity and surface temperature, we can see them as a clump in the color magnitude diagram. So it is easy to detect them in the color magnitude diagram, but only if all these red clump stars are present at the same distance. But we wanted to cover the whole galaxy, and we wanted to locate these red clump stars. So it may happen that the red clump stars are distributed along the line of sight. And along the line of sight, so what will happen due to the distance effect, the lumin or the flux that we receive here on Earth, it will get changed. So instead of clump, we will see a band of color magnitude diagram. For example, in the right side plot, here this is the 2 mass color magnitude diagram of in anti-center direction, and here we can see there are two dense regions are there. And the inset plot represent this represent the population synthesis model, CMD. And in this, we can see that there are different kind of population are present. This RC means red clump star, AGB stars, RGB stars, and as well as low mass main sequence stars, and also foreground population. Here we can see that the second dense region is populated by the red clump stars. There are other kind of population are also present, but most of them, the second dense region here, this is dominated by the red clump stars. So keeping this in mind, we wanted to select these red clump stars from the color magnitude diagram using 2-mass data. So for that, we decided to take a 1 degree by 1 degree region in any direction, let's say in L45 and B5 degree. So we constructed a CMD, 2-mass CMD, and in this, because the second dense region correspond to the red clump stars, so we binned the CMD into the horizontal bins of J magnitude, and in each bin we have plotted color density histogram. So these color density histograms are plotted in each bin to find the peak of the second peak. So we extracted the color of the second peak because this second peak will correspond to the red clump locus. So in this way, we have selected the red clump locus in the color magnitude diagram, which is denoted by here by black points. Now to select the range of stars, so we have used 1 sigma region around this central locus, so which is here denoted by this orange point, and all the stars in this orange point are considered as the red clump stars. So in this way, we have selected the red clump star in a 1 degree by 1 degree region. So here I am showing in different direction how it will work. So in different direction, this red clump locus is not remaining fixed, but it is changing according to direction to direction. This is just because the extinction in different direction is quite different, and we need a automatic way to select the red clump star in each and every direction and covering the whole galactic plane. So we have created a method in which we can automatically select these red clump stars in the whole galaxy, at least in the whole galactic plane. So in this way, if we have selected these red dots, these are all taken as a red clump star candidate. And after selecting these red clump stars, we know that they have a constant luminosity, so fixed magnitude, and considering a constant color range. So we have calculated it was easy to calculate the distance as well as extinction of each and every selected star. So in this way, we have selected the 8.8 million red clump stars in 5800 square degree region, which is bounded by these longitude and latitude ranges only in the galactic plane. And now the catalog is ready. The next task was to validate the catalog, whether the detected sources are really red clump stars and the calculated distance is accurate or not. And in order to do that, we have compared our catalog with many catalogs that are available in literature. And I just wanted to show one to see how the distance accuracy, because we know that Gaia also has provided distance information. And in different catalog data releases, there are different kind of distances that are available in the Gaia. And like RPGO, RGO, these are based on the Bayesian inference using some prior condition. And the distance information Gaia DR3 catalog, they have provided using a multi-parameter fitting forward modeling, and they have provided the distance based on that. So, but there was a paper recently in 2022 by Gaia collaboration where they have compared the distance, all these 3 distances, and found that RPGO based on the photogeometric prior is the best distance indicator out of all these 3. So we wanted to compare our distance with the Gaia distance, which is given by this RPGO. And there was a spectroscopy catalog where we can accurately select the red clump stars from Apogee. So Apogee is a in infrared spectroscopic survey. So they have provided us a catalog of pure red clump stars with 95% purity, and the distance are also in within 5% error. So they have provided us the red clump star catalog. So we compared the distance of Apogee with our catalog and Apogee with the Gaia RPGO to see the distance reliability. So from comparing these 2 plots, we can easily see that there is a very good one-to-one correlation between all 3. But there is a large spread in the Gaia distance when compared to the Apogee as compared to the distance calculated by our method as with Apogee. So this explains that validate our selection criteria as well as the distance estimation method. So our method was great, and also the distance from the Gaia catalog, they can give large uncertainty beyond certain distance. But at that time, the distance from the red clump stars will be more reliable for the distant stars as compared to the Gaia. So this explains the reliability of our catalog. And then the thing that we were wanted to see, that how these stars are distributed, whether they are giving us some structural information or not. So in order to do that, we produced an overdensity map. So this overdensity map, because now we have the position information as well as distance information of all these three stars, so we can construct a 3D map. So we first made the face-on view of the galaxy. And here the color represent the overdensity of these red clump stars. Overdensity means from the density distribution, we subtracted a smoother distribution so as to see what kind of overdensity left, and if this overdensity can relate to some spiral feature or not. And in this overdensity, we saw some curvy feature, which are here seen by blue contours. And this curvy feature, we wanted to see whether there is any correlation with spiral arm or not. So for that, we here overplotted the spiral features that were constrained from other population that I have showed in the third slide. So this red clump star overdensity is very well matching with the outer arm of the galaxy. So this black one represents the outer arm of the galaxy. So there is a very well correlation between the overdensity as well as the outer arm of the galaxy. So this outer arm is beyond the region which was traced or which was accurately traced by the Gaia. And also in the previous plot, this region, this arm was not getting traced because this is a very distant position, and the distance accuracy become very small over there for most of the tracers. But here in the red clump star, we can systematically trace this outer arm of the galaxy. And this was not the only case, but what we see that in the earlier studies, if they are getting signature of the outer arm based on very low number density, they said that outer arm is up to dash dotted line, but we were seeing over density beyond this dash dotted line. So this is a 6 kiloparsec long extension of the outer arm of the galaxy. So this explains that what we have known earlier is not a complete structure of the galaxy. So this in the right side plot, the background map was made based on some observation, but they said the outer arm, extent of outer arm is up to this solid line. But in our study, we are seeing the extent beyond that region. So here we present an updated view of the structure of the Milky Way galaxy, at least the spiral arm of the galaxy. So this is all about the azimuthal asymmetry and the spiral arm of the galaxy. Next thing, we wanted to check the asymmetry above and below the galactic plane. So for that, we analyze the data and done similar exercise, but for the stars that are above the galactic plane and below the galactic plane separately. So the first left-hand image represent the stars above the galactic plane, and right-hand image represent the overdensity of star below the galactic plane. And here we can see that from this dash dotted black line, we can see that a part of spiral arm, outer arm is getting traced or is coinciding with the overdensity in a small part of the galaxy, but the other part of the arm is getting traced in the other part of the galaxy. And this is so relating it with artistic impression. Here we can see that this is explain the stars which are above the galactic plane. So above the galactic plane, a part of spiral arm is getting traced. So a part of galactic spiral arm is present above the galactic plane, and the other part is bending below the galactic plane. So this explains that our disk or the spiral arm are not flat, but they are warped upward in one direction and downward in other direction. So this was a first observation signature that was explaining the warping of the spiral arm. And we knew that this galaxy disk is not flat, but it is warped upward and downward in different direction. But for the spiral arm case, we have never seen that. But in the red clump star distribution, first time we have seen that there is a warping of the spiral arm also. So this warp we have also modeled and compared with the younger population. And that paper is near acceptance. We have submitted the revised version on the last day only. And so that part I will not discuss here. I'll directly go about this all discussion was about the large scale structure of the galaxy. Now, if we wanted to do the small scale analysis, so what will we do? We know that the dust is highly confined to the disk of the galaxy, and it can give us the fine structure detail. Like this is an example of M57 spiral galaxy. This is an external galaxy, and this is its JWST image. So it is a mid-infrared view where the dust is actually emitting. And here we can see that apart from the large scale feature, there are also small scale features are also present in between the spiral arm. So there are large scale spiral arm in our galaxy, but we do not about this small scale feature. There could be this small scale feature like in M57. They are also can be present in our own galaxy, but it is quite difficult to make this kind of map for our galaxy because we can only get the integrated information, and we do not know the distance of each and every dust cloud, so that we can trace this kind of small scale as well as large scale features. And so direct production or direct construction of this image is not possible using the longer wavelength measurement of the dust. But dust has very unique properties also. So the one of them is extinction. So whenever the light is passed through this submicron size solid dust particles, so the light will suffer extinction, like it will scatter the light or absorb the light. So and hence as a result we will see some dark features where the dust is present, like in the galactic plane. And also, apart from this extinction, if this dust particles, they are asymmetrical grains, like elongated grains. When the light from the star will interact with this elongated dust grain, then a part of light, they will suffer differential extinction because of the longer axis as well as shorter axis of the grain. So the transmitted light will be partially plane polarized towards the shorter axis of the grain. Of course, there should be some net alignment of anisotropy, which will be provided by the magnetic field direction. So here this right side plot represents the polarization map of approximately 5,000 stars. And this explains very well that wherever there is a high extinction, the darker region, there are a larger polarization also, because here the lines here represent the polarization vector. The length of line gives the degree of polarization, and its orientation is aligned with the magnetic field or the polarization angle. So here we can see that in the high latitude region, there are less polarization, low polarization, and in the galactic plane where the extinction is high, the polarization is also high. So these are the two properties of the dust. Now, if we can use these properties to find the dust distribution. So for that, what we can do, like we can combine the star polarization information of a star with the distance information. How? This is a cartoon diagram showing if this star is passing through one dust cloud, say, so this the light of this star will get partially plane polarized. But for the next star, it is passing from two dust clouds. If the alignment of the grains in these two directions, in these two clouds are same, then the degree of polarization of the second star will increase. But if there is any deviation, the degree of polarization will decrease. In any case, if we systematically study the polarization as a function of distance, we will see a jump in the polarization, whether increasing or decreasing. And on the basis of that, we can say that, okay, there is a one dust layer should be present here, which is polarizing or which is changing the polarization of the second star. So based on this, we wanted to study the dust distribution using the polarization information. So keeping in this in mind, we choose to select the galactic open cluster, because clusters are the lot of stars, a bunch of stars that are present at the same location. So it is easy, statistically speaking, it is easy to constrain their distance as well as polarization. So we choose to select this galactic open cluster as compared to any randomly or star in the sky. So there are approximately 7,200 clusters that are known till now, but out of that, only 40 clusters that have polarization information, which are marked here by these black dots. And we can see that they are up to a certain distance, like up to Perseus arm only, not beyond that. So these clusters that I have observed with the polarization, so they have distance less than 3 kiloparsec. So we wanted to study clusters, but in the same line of sight that are present at a different distances, because in that way we will study how many dust layers are there in the particular line of sight. With this in mind, we selected the cluster for the observation, and we keep in mind that the location, our location from which we are observing the carrying out the observation, the distance of the cluster, because we wanted to target the longer distance cluster so that we can have all the dust cloud information in the foreground of that cluster, the brightness of the cluster, size, and number of members. All this, keeping all this in mind, we selected 15 clusters in roughly 3 different line of sight. And so the first, this cluster we have selected because there was already some observation of in literature, there are polarization observation in this direction, and we have selected a distant cluster. And all these observations we carried out using Indian observation facility. We have a one in-house polarimeter, that is a CCD based polarimeter. We call it as EM-POL, and it is a back-end instrument on 1.2 meter telescope at Mount Abu. So for this instrument, we have regular 3 to 4 nights per month, and we observed different clusters. And this is the optical layout of this polarimeter, that we have a rotating half wave plate for the modulation, and a fixed half wave plate. Then there is a wire grid polarizer. So this is a single channel polarimeter. And we also observe the some clusters from other institute, that is a ARIES, and using the ARIES imaging polarimeter, we call it as AIM-POL, and it is on 1.04 meter Sampurnanan telescope. And this we were awarded 13 nights in 3 observation cycle, and this is the image of that instrument. And here this is the optical layout, but instead of wire grid, which we are using in EM-POL, there is a Wollaston prism. So it split the light into orthogonally polarized waves, so E ray and O ray. So these two waves are focused on the same CCD plane. So this is a dual channel polarimeter, while the EM-POL was a single channel polarimeter. And the other difference is that in EM-POL we have 3 arc-minute field of view, while in EM-POL we have approximately 8 arc-minute field of view. So in order to appreciate the difference between the two instruments, here I am showing an image of a cluster which we have observed from both the instrument. And this is the Kronberger 69 DSS R-band image, which is from a photometric survey. And this is R-band image. And this is the image from the EM-POL of the same cluster. And this is the image for the EM-POL observation of this cluster. And so here we can see that for each and every star, we are getting 2 images of a star, one corresponding to E ray and other corresponding to O ray. So there was some difference in the reduction pipeline also. So we have developed the pipeline, automatic pipeline for the data reduction from EM-POL as well as from EM-POL. And in next few slides, I will be discussing about the result that we have obtained from all these 15 clusters. So starting with the first line of sight, we have observed this Sterling 3 cluster, and this observation we have done from EM-POL. And here we got 43 stars in the core region of the cluster. And here we can see that there is these lines, dotted line represent the orientation of the galactic plane, while these red color lines represent the polarization vector of all the stars that we have observed towards this cluster. And here we can see that there is a quite deviation of the polarization angle with the galactic plane. So the magnetic field in this region is not kind of aligned with the galactic plane. But next we wanted to study the dust distribution. So we combined the polarization information with the distance information from Gaia. And we have used Gaia DR2, the same RPGO distance on the x-axis. And here plotted the degree of polarization angle as well as reddening as a function of distance. So here in the polarization as well as reddening, we can see that there are 2 jumps in the polarization and reddening. So this explains there are at least 2 dust layers that should be present in the foreground of the cluster. One is at approximately at 1 kiloparsec, and other is at 3.4 kiloparsec. And to confirm whether there is actually such layers are present or not, we checked the literature and we found that there is one dark cloud, LDN 1306, is present towards this line of sight, and it is present at 1 kiloparsec distance, which is foreground to the cluster. So the first cloud, which is at 1 kiloparsec, we were seeing a jump in polarization as well as extinction, explain and that there is actually a foreground cloud is present. And second was also present, but we could not find a dark cloud over there. But we used the kinematic distance from the CO data as well as H1 data, and the radial velocity peaks shows that the kinematic distance from those radial velocity measurements shows that the distance is very well aligned with the distance what we have found from the polarization observation. So this validates that it is the polarization technique is very good to obtain the distance of the dust layers that are present in a particular line of sight. So we carried out this and we then combined the distance polarization information of all the stars within 15 degree that were observed in the literature and combined with the distance information to see the large scale distribution of the polarization and if it can give us some hint to the structure or not. So for that, these different symbols, colored symbol represent the stars towards different cluster. And here we can see that there is a increase in the polarization till 1 kiloparsec. There is a uniform increase. So this was expected because the dust is distributed uniformly in the solar neighborhood. So up to 1 kiloparsec, we are seeing a systematic increase. But at 1 kiloparsec, there is an abrupt rise in the polarization, which explains there should be a dust cloud which is present just below 1 kiloparsec, which is polarizing the background stars. But after that, there is a very low number of stars in each cluster direction between 1 and 2 kiloparsec gap, which is here denoted by this dashed line. And interestingly, the polarization, the average polarization before and after the gap is almost same. So this explains there is a very less dust content in between this gap, which is polarizing a background starlight. And to see whether this number density of the stars are actually low or this is biased because of our selection criteria, we checked the 2 mass data and plotted the number density with the in distance, and we exactly see a dip in the number density of stars in between 1 to 2 kiloparsec. So there is a less dust content, less number of stars, so there is a inherently less material is present. So in that way, we are exactly probing the interarm region between the local arm and the Perseus arm, where and there is intrinsically less dust as well as less amount of stars, less number of stars are present in that direction. So this gives us the confidence that we can actually trace a structure or small scale as well as large scale structure using the polarization. So as a next step, we went to the other line of sight, and this is one of my favorite because we selected this line and close to the anti-center direction. Here, here the amazing thing is that if we have some kinematic information from some molecular data in longer wavelength, we still cannot find the accurate distance of the dust cloud along this line of sight because the major portion is in major portion of the velocity component is in the plane of sky, but not in the radial direction. So the distance estimated based on their radial direction will not give us the accurate distance of the dust cloud that are present, that are getting traced in the longer wavelength. So polarization is the one of the best way to find the distance of different dust cloud in this direction. So we have observed 5 clusters that are present at different distances, and there was already observation of 5 clusters that are at nearer distances. And the observation shows that we have approximately 100 stars towards each cluster direction. And here I am showing the vector diagram of towards each cluster, polarization vector plot. And there are some some interesting features, like in Berkeley 71, there is a very nice rotation of the polarization angle, which is connected to the foreground star morphology. That's why we are getting this kind of thing. But I will not go into detail because our motivation was to see the dust distribution. So we combined the whole polarization data with the distance information to see the dust, how many dust clouds are there and at what distance they are located. So we have done this exercise with Vincent using his algorithm on Bayesian inference of starlight polarization based. And here we are interestingly finding that in each line of sight we are finding different at least two dust layers that are present before the cluster. So these plots represent how the Q and U, the Stokes parameter, are varying with the distance modulus. So any change in the slope will give us the hint that there are dust layers are present. Because of that, there is a change in the polarization of the star behind that dust layer. And combining all these information into one plot. So what we are seeing in the right side plot is the cloud distance that we are getting at least two clouds or the three clouds in each line of sight. So this is the in x-axis, this is represented cloud distance towards that cluster, and y-axis is the latitude range, or we can say that the cluster. And here, interestingly, what we are finding is that all the clusters these two and this, they are showing the cloud distance which is matching with the spiral arm of the galaxy. So the local arm, the Perseus arm, and even the outer arm of the galaxy. So most of the polarization information or the changes that are occurring due to the dust present in the spiral arm. So if we can somehow trace this is only in the one direction. So if we can somehow trace the whole galaxy and in this direction, so we can get the information about the spiral arm, and in that way we will be able to trace the complete spiral arm of the galaxy. And at last we targeted the tangential direction. The anti-center direction is perpendicular to the spiral arm of the galaxy, but we wanted to see how the polarization behave when we target the cluster in the tangential direction. So it is not crossing the spiral arm, but they are parallel to the spiral arm. So here we have observed 9 clusters, and in different direction and different distances. So I will not show the detail of each and every cluster, but in combination, what we are finding is that in each line of sight, in anti-center, in this direction, as well as in tangential direction, we are getting different polarization pattern, how the polarization behaving with distance. So in anti-center direction, it was increasing if we combine the data of all the cluster and all the stars that are available. So it is increasing with distance, and the polarization angle is approximately constant after a certain point. It is approximately constant. But in this direction, the polarization is increasing, but with a lot of scatter, and in the polarization angle also, we are getting a large scatter in the polarization angle. So what could be the possible case? It has been observed in many external galaxies that the magnetic lines and the magnetic field is oriented parallel to the spiral arm of the galaxy. So if similar is the case in our direction, our galaxy, so what will happen if magnetic lines are parallel to the spiral arm of the galaxy? So in the polarization measurement, we can only measure the plane of sky component of the magnetic field. And in anti-center direction, majority of the magnetic field will be in plane of sky component, and there will be very less component along the line of sight, which we cannot measure using polarization. And so we are actually seeing the magnetic field, actual magnetic field direction using the polarization. And here, if we look closely, that in this line of sight, at different distances, the magnetic lines are parallel to one another. So if they are having same orientation with distance, so we will get an increase in polarization with distance, and the polarization angle will remain almost constant. So this is what we are observing in anti-center direction. But as we came to this tangential direction, so what is happening in our direction, in our line of sight, the magnetic field is almost parallel to our line of sight. not in the so we are, because we are measuring the plane of sky component, and the majority of the magnetic line in this direction is parallel to the line of sight. So the component which is perpendicular to the line of sight, or in the plane of sky, is very small. So any small change in that component will affect drastically the polarization behavior. That is why with increase in the distance, the magnetic lines or the orientation of magnetic field is changing, and hence we are getting a large scatter in the polarization angle. So we are still working on this, and to test that whether this is actually the case or not. But more or less we are confident that magnetic lines or the magnetic field is oriented parallel to the spiral arm of the galaxy. Only that we are seeing this kind of high scattering in the polarization towards the tangential direction as compared to the anti-center direction when it is perpendicular to the line of sight. So the polarization information are not only providing us the information of the structure or the spiral arms, large scale structure or small scale structure, but they are also giving us a hint about how the magnetic field is oriented in our galaxy. So if we have, this is only in 3 line of sight, if we have observation of over the full galaxy, so we need a Pacify kind of survey, but in the galactic plane, so that we can trace the magnetic field as well as the structure of the galaxy. So here I'll summarize my talk, that to have complete understanding of the morphology of the disk, we need to study different age population, their distribution, their chemistry and dynamics, to completely understand what is going on in our galaxy. And here we have represented that RCR, red clump stars, are very good distance indicator as well as structure tracer, and we have founded the distant arm of the galaxy, that is the outer arm of the galaxy, and with 6 kiloparsec long extension as compared to the earlier studies. And also these are catalog, and the observation shows that it is the spiral arm of the galaxies are not flat, but they are warped in one direction upward, in other direction it is warped downward. And this is based on the stellar distribution. And apart from this stellar distribution, dust is a very good structural tracer. And if we can probe the structure of the galaxy using dust, then it will be best. Like the polarization is a very efficient and indirect way to trace the structure of small scale as well as large scale structure of the galaxy, and also give us hints about the magnetic field orientation within the galaxy. So with this, I'll thank you all for listening and inviting me to deliver this talk.
Thank you, Namita. Thank you so much. Are there any questions for Namita? There is a question by Nikos. Nico, you want to unmute?
Yes. Hello. Thank you for the talk. Sorry, I was not able to join from the beginning, so I don't know if you've mentioned anything about it. But would a survey like GPIPS be helpful for what you're doing, which is infrared polarization? And it is in the galactic plane.
Yes. Hi, Nick. Of course, that will be helpful to say that whether their polarization is in this direction, how it is behaving. But my concern is that it is infrared polarization, and in this direction there's very low polarization, as well as we are seeing the large scatter, and in infrared the polarization is again decreasing according to Sikorsky law. So it will be helpful if we can probe the same thing using the optical polarization, because in that way we can at least have a good signal to noise ratio for the polarization observation. But definitely there will be something, and we are trying to look at the GPIPS data and trying to find that how the magnetic field is oriented using the polarization information.
Thank you.
Vincent?
Hi, thank you for the talk, Namita. Could you go back to, I think it's the previous slide where you showed the difference, this one?
This one?
Yep, this one is good. So am I correct in saying that P increase, like continues to increase when you look in the anti-center direction, while it seems to increase and then eventually decrease when you look tangential to the spiral arm?
It is definitely increasing towards anti-center direction because it is supposed to increase if the magnetic lines are parallel to each other. So the polarization of every next component should increase. But in tangential direction, what is the actually the problem is that this is not crossing the spiral arm, and most of there will be a small scale features like what we can see in the M57 galaxy. There are many small scale features, and if because of the magnetic field is parallel to the line of sight, so and with each distance the magnetic lines, like in this, magnetic lines are parallel, and with distance they are changing. So we expect that there will be random distribution of polarization as well as in polarization angle. So because it spans also a large latitude range, so there could be small scale features that are giving rise to this increase and then large scatter. So we have to see in very small, a narrow slice in the longitude and in the different distances, how they are changing.
Okay, so somehow your interpretation could be that you might be more affected by, let's say, turbulence or indeed small scale structures when you look tangential, because the mean field gives zero polarization, basically.
Yes, I think that is the reason.
Cool, thank you.
Thank you.
To follow up on that, if I may, I'm also noticing that the tangential magnetic field, the polarization in the tangential line of sight reaches 10%, right?
Yes, but I think I made a cut on like 1 sigma detection, so could be that there will be high error for those polarization measurement. I have to clean the data to see it more clearly.
Oh, okay. Because I would be surprised if the tangential direction gives you higher polarization than the one in the anti-center where you mostly probe, right, the plane of the sky.
Right.
Okay, thank you. There is another question by Vasilis.
Hi, Namita, very interesting talk. I was just wondering, this may be a bit off topic, right? But since globular clusters are interesting for a number of reasons, would you consider that since we know that all stars there were created at the same time, if one were to measure with a new instrument, for example, the polarization of many stars in the cluster, and given that they are at the same distance, you could efficiently identify polarized stars themselves, that could be of interest in a statistical sense to identify which stars in a cluster appear polarized and which do not?
Yes, definitely the polarization, that will be intrinsic polarization, because I suspect that interstellar polarization, because globular cluster are mostly present in the halo, so high latitude there will be less dust to have some interstellar polarization. But of course, for intrinsic polarization, that will be good to find. But if all the stars may not have some intrinsic polarization, and if we can constrain the distance, and based on distance and polarization, I'm not very sure, but definitely using polarization, we can find the intrinsic polarization of those stars, and Pacify, I think, is the best for doing this job.
Yeah, thank you.
As a follow-up question, do we know anything about dust and magnetic field in clusters? Like, is there some dust? Because you may have like an intrinsic scatter within a cluster,
Yes, but I intrinsically choose my, there could be, like, there are many papers, I think, on that also, that how the dust is distributed in the cluster and what is their effect. But I have chosen for my study, I have chosen mostly the AZ clusters, billion years or giga year clusters, so that they will not, we are not expecting to have dust at that long time. So most of the information what we are getting should be from the interstellar polarization. There could be some stars in the line of sight that may be giving some interstellar polarization. But in the cluster, we are not suspecting that they should have any intrinsic polarization. I hope I am answering it correctly. Like, this is what you wanted to.
Yes, thank you.
Okay.
Are there any other questions for Namita? Okay, I don't see any more hands, so let's thank Namita again for this nice talk, and thank you all for coming. Have a
Thank
good evening.
you. Thank you all for listening and having me here. Thank you.
Okay.
Bye.
Thank you. Bye bye.